Okay, good afternoon, everyone. Thank you for tuning in today. Today we will be discussing the Llama V01, rethinking step-by-step visual reasoning in LLMs. And as you can probably tell by the title that, first of all, this paper introduces a new model named the Llama V01. And this paper also discusses the reasoning in LLMs, more specifically visual reasoning. We'll get more into that later. Okay, so introduction. What does this paper talk about? Or like, what are the main things or main points of this paper? First of all, it talks about step-by-step visual reasoning and complex problem solving. So most models that are available right now, or most small models that are available right now, currently focus on uh, like solving the thing without breaking it down. So this paper talks about how you can make the model think in steps, or basically breaking down the task into manageable parts, or like smaller parts. Okay. Second of all, the role of LLMs. How do LLMs play in here, and how they're increasingly focusing on integrating visual reasoning into LLMs, and the challenges in benchmarks. Currently, a lot of benchmarks only focus on two things, which are speed and accuracy. There isn't really a benchmark available that, or there wasn't really a benchmark available that focuses on reasoning or step-by-step reasoning, or how the model thinks. This paper also introduces the LlamaV-o1 model, which is a new model that can uh, combine both curriculum learning and beam search. Again, more into that later on, and the future impact, and how this paper enhances the AI's ability and interpretability into real-world reasoning problems. Okay, so what are the problems that are being discussed in this paper? First of all is the lack of step-by-step visual reasoning. A lot of frameworks right now only prioritize single-step reasoning. So basically, a complex task such as like a hard differential equation and a simple algebraic equation would probably be solved in the same number of steps by most models. And can lead to this can lead the model to fail uh, in solving the question correctly. So this paper addresses that. And secondly, the insufficient benchmarks. There aren't enough benchmarks, or there isn't a good benchmark that measures the reasoning of the model, or the step-by-step uh, tokens of the model. And the need for structured reasoning. So this paper proposes a framework that focuses on the necessity of, first of all, it needs to be structured, and step-by-step approaches to enhance problem solving effectively. And lastly, the goal of enhanced solutions. It addresses these gaps, aims to develop more robust AI systems capable of tackling complex real-world problems. Okay, so what did this paper offer us? What did we get from this paper? First of all is the VRC bench, or the Visual Reasoning Chain Benchmark, which is uh, uh, which is really good for evaluating step-by-step reasoning or multi-step visual reasoning tasks. And the novel quality metrics. It's a new metric that assesses or gives an assessment of visual reasoning quality at individual steps. So it looks at each step that the model makes, and it focuses on how well that step was structured and the coherence of that step. And lastly, they also made the LlamaV-o1 model, which is a multi-model reasoning model that integrates both visual and textual information. So first of all, the Visual Reasoning Chain Benchmark, or the VRC bench, which evaluates visual reasoning abilities in AI models. And it does that across multiple complex scenarios across in multiple distinct categories. And the structure of it is that it's divided into 8 distinct categories, Each represents different reasoning challenges. And so what are these categories? First one is object recognition, how well the model can identify objects within an image spatial relationship. It understands how and where the objects are placed when compared to each other or relatively to each other. Attribute understanding. It recognizes and interprets object attributes, so like the color, size, shape, and so on. Counting, it can count how many objects there are in there or in the image. And there's also causal reasoning and temporal reasoning, which causal reasoning just it infers basic outcomes based on visual cues and object interactions. Temporal reasoning it understands the sequence and time-related relationships in the visual data or in the image. Relational reasoning it tries to understand the relationship between the objects that are in there. So if two people are in there facing away from each other or walking away from each other, it will probably tell you that they're not really friends. But if they're facing each other and talking, then there is probably a type of relationship between them. And a multi-hop reasoning that tries to integrate information from different parts of an image to get you to a conclusion. So the visual reasoning the reasoning steps or the visual reasoning steps. The benchmark typically includes 1 to 10 reasoning steps per challenge, and this depends on the task's complexity. So again, a simple uh, math problem from Math Vista, for example, would probably be solved in like a step, but a more complex one would probably be solved in 4 steps. The most complex one, or like the most complex task in here, would most likely be solved in like 10 steps or so. The assessment goal, like how can it assess the model? What does it focus on? It provides a comprehensive evaluation framework that ensures that the AI model can interpret visual information in a similar fashion to human reasoning. So if the model does so in like a way that's not the way that we're used to, we're probably going to have it focus or redo the task until it can do it in a manner that we can understand it in, or understand the steps in. And visual representation. So tables or anything that can illustrate the categories and examples. And it also focuses on enhancing understanding of the benchmark's diverse challenges and the significance of the research. It serves as a critical tool for advancing AI research, particularly in improving visual reasoning capabilities and interpreting complex visual environments. Okay, so now we're going to talk about the Llama model or the LlamaV-o1 model. Okay, the introduction of the LlamaV-o1. It is a state-of-the-art model designed for multi-step reasoning. So this model was designed with uh, step-by-step reasoning in mind, and it focuses on enhancing logical progression and contextual understanding. Again, this is what it was built on, or what was in mind when building the model. And then the structured training paradigm. It utilizes a systematic approach to develop reasoning capabilities and trains on a diverse data set across various domains for broad applicability. So you can use it in medical reasons, or you can use it for math, you can use it for, um, I don't know, for English and literature, for example. These are some, like, it was built upon diversity. Okay, what are the features of this model? It maintains coherence over extended dialogues. So you would not find this model hallucinating, or to be more precise, the hallucination in this model is going to be less than what you'd expect from different model of the same size. And it processes individual queries while drawing connections between them. So again, it tries to build connections, relationships between different tasks in the same task or different subtasks in the same task to make sure that it understands everything well. And it ensures that information remains relevant across multiple interactions. Again, so it wouldn't try to go way too far from where it originally started. Okay, what are the benefits of multi-step reasoning? It's ideal for complex tasks such as problem solving, decision making, and narrative understanding. It also enables the model to generalize effectively in real-world scenarios. Okay, now the novel evaluation metrics. Okay, so first of all, we're going to talk about faithfulness. The faithfulness step ensures reasoning steps align with the source reasoning chain. And the faithfulness token, it extends the faithfulness step to token level accuracy for in-depth validation. Okay, so what does this mean? First of all, the faithfulness step, it tries to ensure that the model or the steps that the model makes are all similar to each other or all following a line of thought or a chain of thought. The faithfulness token extends that into tokens or focuses more on the tokens that the model generates. The informativeness step measures whether the reasoning process extracts all relevant information from the context. Again, that's pretty straightforward. Repetition and redundancy. The repetition token identifies unnecessary repetition or paraphrasing in reasoning steps. So anything that's not relevant or anything that's being repeated, it focuses on that. Redundancy detects redundant reasoning steps that do not add any value. Hallucination detects fabricated or irrelevant reasoning steps that are not aligned with the source. Semantic coverage step ensures that all essential semantic elements from the source reasoning are included. The reasoning alignment evaluates the overall coherence and consistency between the AI-generated reasoning chain and the reference steps. Common sense reasoning checks if the AI applies common sense knowledge in the reasoning step. The missing step, it checks whether there's a missing step. Like, that's pretty straightforward. So the step-by-step visual reasoning model. Uh, the model is trained for improved reasoning. It starts with foundational tasks or like basic tasks and then advances to multi-step reasoning, enhancing logical coherence. This helps the model handle complexity and generalize effectively to challenging scenarios. Scalable inference with beam search. This implements a parallel beam search strategy for efficient inference, and from there, it selects the most optimal one and ensures high quality outputs while reducing the computational cost and achieves constant scaling versus linear scaling of traditional approaches. So this model applies curriculum learning. What is curriculum learning? Curriculum learning. Uh, Curriculum learning involves teaching the LLMs progressively from simple tasks to complex tasks, similar to the way we do in schools. So you'd start off with simple math, simple English, simple sciences, and from there you advance to calculus, biology, chemistry, and literature. And I begin by understanding fundamental connections between different modalities, like linking text with images before progressing to more complex scenarios. And this is useful in the sense that it enhances generalization and prevents catastrophic forgetting. Catastrophic forgetting is when, let's say, you teach a model how to do math tasks, and then you move on onto science. Once you do that, and like the model starts to understand the science, it would forget the math. Now, this prevents that and makes the model more coherent and more likely to retain the knowledge that it learned. Now, the multi-step chain of thought. This enables the model to break down the most complex of tasks into simpler, smaller, and more manageable steps to ensure logical transparency. Uh, this approach is mainly uh, copied from humans, uh, ability to problem solve, which would then improve the interpretability in AI. Okay, so what are the stages that the AI is taught while doing the multi-step chain of thought? So it starts off with task understanding. It tries to understand the task and the context given to it, and then summarizes the task, summarizes the task, and this involves generating a summary of the visual data that it sees, and then detailed caption generation, where it would give labels to the things that it sees in the images or in the chart or the infographic that it sees. And then the logical reasoning. The model logically structures its reasoning by simplifying the task for a systematic approach. And then the final answer generation. The model would output the final answer based on reasoning or based on the steps that it went through, which the steps we just discussed. Okay, how do we do all of that, or how is the model trained to do all of that? Okay, so this is mainly broken into three stages: training for summarization and caption generation. In the first stage, the model learns to generate reasoning, summary, and detailed caption describing key aspects of the input data. Using structured training from the CAP-QA split of Pixmo and Geo 170K datasets, it improves its ability to break down multi-step tasks into simpler components. And in this step, it does not do anything other than basically breaking down and giving captions. It does not try to give a final answer. In the in the second stage or in the second step, it is trained for detailed reasoning and final answer generation. The model builds on stage one foundation, learning to generate detailed reasoning steps and derive the correct answer using multi-step interactions from the LlamaV-o1 dataset. And this incremental learning approach refines the model logical flow, improving its interpretability, accuracy, and performance in complex multi-model reasoning. And the way this model is trained is that it uses the Pixmo and LlamaV-o1 100K datasets for training and employing a curriculum learning strategy combined with supervised fine-tuning. I'm sorry, in here, I forgot the third step, which is the final answer output, where basically it would give out the final answer or give out the final uh, reasoning or uh, whatever the model got to at the end, it would give it and output it. Okay, so the model training or the way that this model was trained is that uh, the Pixmo and LlamaV-o1 100K datasets are used for training, employing curriculum learning strategy combined with the supervised fine-tuning on the Llama 3.2 11 billion vision instruct model. And fine-tuning involves parameter optimization to adapt the model to structured reasoning tasks, with training conducted on high-performance computation node using the 8 NVIDIA A100 GPUs, beginning with the Pixmo dataset to develop foundational reasoning skills. Beam search, simplified output design. This approach does not require high extensive output format, and the flexibility makes reasoning process a bit more simple in turn allows which in turn allows the model to focus more in creating a high quality final answer without the expense of forming long structural constraints. This allows the model to be more adaptable to a wide range of scenarios. So it does not really have to focus on just one thing like math or English or science. It can do them all. And the way that they're optimizing inference efficiency through beam search is that the approach does not require a highly extensive output format. So they can keep the output or the final answer as simple as possible. And this in turn makes the reasoning process more simple, which allows the model to focus on creating high quality final answers without the expense of forming strong structural constraints. This allows it to be more adaptable to a wide range of scenarios. And this also gives it improved efficiency. It allows for multiple reasoning paths, and then the most efficient and logical path is chosen. So it would have multiple train of thoughts, and the most efficient one is the one that gets chosen. And the way that they tested this or proved this is through experiment. For the experiment, they used the Llama 3.2 11 billion parameters vision instruct model as a baseline for the experiments. And the Pixmo subset and LlamaV-o1 100 datasets were used for training, and performance was assessed using the VRC bench and six other multi-model benchmarks to demonstrate significant improvements or the improvements that were made in general in reasoning and inference efficiency. Okay, how did they set it up? The baseline model, which is the Llama 11 billion parameters model, is fine-tuned using the Llama recipes framework, which is a supervised fine-tuning method, implementing a curriculum learning strategy with datasets like Pixmo and LlamaV-o1 100K to enhance multi-step reasoning. The model is assessed using six well-known multi-model benchmarks, which assesses mathematical and scientific reasoning, and visual questions, answering, and hallucination handling, as well as the VRC benchmark. And to guarantee equitable comparisons, we employ the VLM eval kit framework and a fuzzy evaluation approach, which GPT-4o serves as the judge, offering reliable evaluations of the outputs produced. Okay, what were the results? The LlamaV-o1 model, which is the model that they were working on, got a final score of 67.33, which is more than the baseline that they set for themselves, and it's more than any other open source model, as well as almost all the closed source models, with the exception of GPT-4o. And then here's a comparison with the LlamaV-o1. So as you can see, it was given a task of where is the game being played, and a picture was given to it. Now, the answer that it was expecting is the game is being played outdoors on a sidewalk. LlamaV-o1 gave a final answer of in the park, and the LlamaV-o1 gave a final answer of the game is being played on a sidewalk in a city or town. And this was the answer that they were looking for. Okay, so what can we take away from this paper? It presents a novel approach to multi-model reasoning, including a new benchmark, metric, and model trained using curriculum learning. It also focuses on tasks that are considered to be rather difficult, and the model efficiently achieves state-of-the-art performance. Generalization and robustness are enhanced by gradually constructing foundational skills, and the outcomes also show how well organized training effectiveness, inference, and comprehensive evaluation works, emphasizing the value of comprehensible sequential reasoning when taking on difficult subjects. Thank you for attending today, and you can check out the paper from this link over here.